Okay, good afternoon. I am now on lesson 58. Lesson 58 on my channel. No, on my channel, lesson 58 on the topic integral calculus. Okay. Lesson number 58 under integral calculus. This is plane area, still polar coordinates. I will give you some more good example problem in the computation of area under polar equations. Okay, I will read the problem. This is the problem, guys. Find the area enclosed by. The given polar equation is R equal to A cosine of 3 theta. This is the polar equation, guys. It's R as a function of theta. It's a polar equation. We are asked to find for the area enclosed by this polar equation. R equal to A cosine of 3 theta. A is not given. Supposed to be A is a constant. It could take any positive number. Okay, let's try to bring out the graph of this polar equation. To bring out the graph, we will use point plotting. It's actually a tiring, very tiring solution, but it's very accurate if we want to bring out the correct graph of the required or of the given polar equation. So I will place it here. I got 4 columns here, guys. Theta, 3 theta, cosine of 3 theta, and the 4th column is the radius r. We got a 3 theta here and cosine of 3 theta. How come this is 3 theta? The given angle is actually 3 theta. Okay? And the sine function of the 3 theta is actually cosine. So I place it here, cosine of 3 theta. Why did I place 3 theta and cosine of 3 theta? So I could watch for the fluctuation in the value of the cosine value of 3 theta. Okay? The fluctuation in the value, because the fluctuation in the value of cosine of 3 theta multiplied by A will represent the radius. So I will know what will happen to the corresponding radius after placing the value theta and cosine of 3 theta. Okay, let's proceed with the point plotting, guys. This is from 0 to 360 degrees with an increment of, the increment is not consistent. I place it here, 0, 30, 45 degrees, 60, 75, 90, 120, 150, 180, 210, 240, 270, 300, 330, and 360. That's a complete revolution. So after assuming a value of theta for one complete revolution, then I will take the value of the cosine value of that angle. I could compute for the corresponding radius as theta moves clockwise or counterclockwise. Okay? So I could point or I could place the point on the polar coordinate system. Okay. When theta is 0 degree, 3 theta will be 0. Okay. Cosine of 3 theta will be 1 because cosine of 0 is 1. So the corresponding radius will be, actually we are using this when we go for each column, okay? If theta is 0, 3 times 0 will be 0, cosine of 0 will be 1, so the radius will be A times 1, or the radius is actually equal to A. And what is the significance of the value of radius is equal to A? The meaning of this, when theta is 0 degree, the corresponding point on that polar equation, the radius is actually A. Meaning, when theta is 0 degree, the point, the first point we are looking for is actually this point here. And what is the value of that point? It is A. Okay, this is A. Okay, let's proceed with 30 degrees. When theta is 30 degrees, 30 times 3 will be 90. Okay, so what will come out will be cosine of 90. Cosine of 90 will be 0. Cosine of 90 will be 0. So the radius will be A times 0. But what will come out at 30 degrees? The radius is 0. What will be the significance of that? When theta is 30 degrees, this is 45, right? 30 degrees is a little bit lower. When theta is 30 degrees, this one may be, the value of the radius is 0. So it is coming from A, then it goes to 0. So how do we know the shape of the curve between A and this point here? Later on, we could visualize. Okay, let's continue. When theta is 45 degrees, 45 times 3 will be 135. Take the cosine of 135, that will be a negative value. It is negative 0.707. The value of the radius at that angle. When theta is 45 degrees, cosine of 3 theta is negative 0.707. And the radius will be A times negative 0.707. Or the value of the radius is negative 0.707 times the value of A. There's a negative sign over here. There is no such thing as a negative radius. The significance of this negative here is that instead of going to the original direction, take the reverse direction. So actually, when theta is 45 degrees, this is 45 degrees. What will come out from our computation for the value of the radius is actually negative 0.707A. This is the point. Okay? So actually, the graph comes, the direction is something like this, guys. Okay? Then it goes here. You see it? It's just like a tomahawk missile, okay? When theta is 60 degrees, 3 theta will be 180. Cosine of 180 will be negative 1. The radius will be negative A. The radius at 180 is actually negative A. There is no such thing as negative radius. The significance of this, just reverse your direction. When theta is 60 degrees, this is supposed to be plus A. But since the sign of the radius after the computation is negative, it should not be here. It should be the other way around. This is negative A. Because if what we computed is plus, we put plus A over here. But since the computation bring out a negative value, it should not be here. It should be the reverse one. This is negative A. Okay? So that is actually the graph, guys. Okay? When theta is 75 degrees, 3 theta will be 225. Cosine of 225 is on the third quadrant, negative value, negative 0.707. The value of radius at 225 is negative 0.707A. When theta is 45 degrees, the value of the radius is negative 0.707. Negative. It should not be here. It should be here. This is negative 0.707. Negative. 45, you just extend it, then place a radius value of 0.707 times A. So actually, this is the direction of the graph, guys. Okay, you see it? Then when theta is equal to 100, what's next? 90. At 90, this will become 270. Cosine of 270 is 0. At 90 degrees, the radius is 0. It goes here. So actually, the graph goes something like this. You see it, guys? Right? Then as we continue this one, the graph will go up like this. Okay? This is 0.707A again. This is 0.707A. And this is A again. Okay, this is A. This is A. This is A. So actually, the required graph is a 3-petal flower. Okay, so emanating from this zero here, it goes up here. It goes up here, go down here, go down here, go down here, go down here. Okay? Then it will reach the zero here, then it will go back to the original direction. That's it. That's the complete graph. So it starts from here, it will go here, okay? It will go here, up, down, then up. And that's the complete graph of the equation R equal to 8 cosine of 3 theta. And we are required to find for the area bounded by this 3-petal flower. So actually, we could use symmetry. Just take 1/2 of this, okay? Then times 6. This is 2, 4, 6. Okay? So, let's bring out the solution now, the integration process. Differential area is 1/2 of r squared differential theta, okay? For polar coordinates. What is r? R is actually a cosine of 3 theta. Squaring both sides, r squared will be a squared cosine square of 3 theta. But we know from identities that later on we could not integrate this one. So we will try to replace this one as a function of a double angle. Okay? Cosine square of theta from a trigonometry is actually 1 plus cosine of 2 theta all over 2. So if we try to compute for the value of cosine square of 3 theta, we will follow this. All angles here should be multiplied by 3, so we could attain this one. So cosine square of 3 theta, you multiply this theta here by 3, so it will become 3 theta equal to 1 plus cosine 2 times 3 theta. 3 theta is 2 times 3 theta will become 6 theta all over 2. Therefore, the equivalent of r square in terms of a double angle is actually, we will follow this. Where is it? R square, this is what? R square will be a square over 2. There is an over 2 over here, I bring it out. Okay, there is an a square, so this is r square is actually a square over 2 times the quantity 1 cosine of 6 theta, equation number 4. Therefore, to take the total area now, total area, this is actually the differential, the integral. The integral of the total area is equal to 6 times r squared differential theta. We have computed for this as a function of a double angle. It is this, right? And what will be our limit? Our area is 6 times, so we will just move the horizontal slice from 0 to the limit of this one. When the value of the radius is 0, it is actually 30 degrees. So our limit is actually from 0 to 30 degrees, then times 6. 1/6 of the area, the limit is from 0 to 30 degrees. Okay, that's 1/6 of the area. So to compute for the total area, this is multiplied by 6. Okay, so this will now be equal to 6. This is 2 times 2. 2 will cancel out here, so we bring out the constant. This will be 3/2 of a squared, the integral from 0 to 30 degrees. We bring out this one, guys. It is here already, okay? The integral from 0 to 30 degrees of the quantity 1 plus cosine of 6 theta differential theta. This is integrable, this is integrable. But the 6 theta here, u is actually 6 theta. du will be equal to 6 differential theta. So we are missing 6 inside, so to bring out the integral, we introduce 1/6 outside. So this will now be 3 halves of A squared. I am following this. 1 times differential theta, the integral will be theta. The integral of a cosine is actually sine, but we must have to introduce 1/6 outside. So this is 1/6. The integral of cosine is sine. Sine of 6 theta with the limit from 0 to 30 degrees. Okay? Let's convert the given angle in degrees to radians. Pi radians is 180 degrees. We dividing both sides by 6, this is pi over 6, will be 180 over 6. Oh, what is 180 over 6? It is 30 degrees, it is 6. So actually 30 degrees in terms of radians is pi over 6. The significance of this pi over 6, if we try to substitute it on the limit, it will be the correct specification. It will not be in degrees, it should be in radians. So this should now be 3 halves of A squared. Okay, let's now place the upper limit times theta, pi over 6. Okay? Let's compute for the value of that one. Sine of 6 theta. 6 times pi over 6. Right? This one. 6 cancels. So this will be sine of pi. But what is pi? 180 degrees. Sine of 180. Sine of 180 is actually 0. So this is 0. That's the upper limit. Minus open quantity. We will follow this. We substitute for the value of theta for 0. So this will be 0. When theta is 0, this will be 0. The value of this, 6 times 0, 6 times 0 is actually 0. Okay? And if we take the sign of 0, it will still be 0. So this is 0, this is 0. So actually what comes out is this. No more lower limit. The second value on the upper limit is also 0. So what comes out is actually like this. 3 halves of A squared times pi over 6. Okay, this 3 here cancel with this. So what will come out? There is an over 4 on the denominator, right? So this is 1/4 of pi A squared. So the area of the 3-petal flower is actually 1/4 pi A squared square units. The area covered by this 3-petal flower, okay, is 6 times this area here, and after the integration, what comes out is 1/4 pi A squared square units. That's it, guys. It's very interesting. If you, the only problem is actually on the point plotting. If you could not plot the graph correctly, okay, you will be lost because you don't know what will be your lower limit and upper limit, and will it be a symmetrical figure, because we do the point plotting step by step with an increment of not so big. So actually we were able to plot the graph correctly. From 0 it goes here, then it goes here, it goes up, it goes up, it goes down, then it goes up. So actually the polar equation is actually symmetrical. Okay? Symmetrical. This area here is same as this, same as this. So if we take half of the area, then we multiply it by 6, that represents the total area of the 3-petal flower. Okay, that's it, guys. Good afternoon, Los Angeles.